The Transport Control Protocol, or TCP, is the most commonly used transport layer protocol on the Internet. Let's take a look at some of the factors and or properties and the way TCP works. You might remember from your basic networking course that we never have really built anything that uses the OSI 7-layer model. TCP and IP were actually implemented with more of a 4-layer model. In this case, we are interested mainly in these three, the lower three layers of the TCP IP stack. The transport layer is the realm of TCP and the user datagram protocol, which we'll talk about later. Just as a reminder, a protocol is an agreed upon specification or format for transmitting data between two devices. Without these protocols, we couldn't have meaningful communication. So we have agreed on the format of the packets that we're going to send and what type of information is going to be in the headers of these packets that we're sending. And that's one of the things we're going to talk about today is what is in these headers. So examples of protocols are TCP, which we're going to talk about today, the user datagram protocol, which is also a transport layer protocol. It's much simpler, but it's also still very important protocol. The IP protocol, the Internet Control Message Protocol, or ICOMP, the Address Resolution Protocol. There are actually scores of these different protocols. These are ones that are used probably the most. So let's talk more about the TCP, or the Transmission Control Protocol. TCP is responsible for breaking the data into segments, setting up a connection between two devices, encapsulating the data segments in such a way that they can be properly reassembled on the other end, and making sure that the data is received by the other device. So these are all very important functions that the TCP protocol are going to do for us. And we're going to talk about how it does these things. Now, here is the TCP header format. I think I got this directly out of the RFC, the request for comment document that actually specified the format of TCP. A couple of things I want you to remember here. The numbers across the top, these are bit numbers. And this header has been folded. We're showing you 4 bytes or 32 bits across, and then we fold it so that this is bit 30, this is bit 31. This bit right here is actually bit 32, and that will run through 63. So this bit right here is bit 64, etc. So we have folded the header format here just so we can show it on a single page. In the real world, the contents of a packet are ones and zeros, a stream of ones and zeros, and the receiving device breaks these into pieces based on where particular numbers of bits, and then maps these the contents of that onto these header formats. And the same thing happens on the sending end, the source end. So this goes back to this idea of a protocol, where we're deciding or we're agreeing on which numbers of bits mean one thing versus which bits mean something else. So keep in mind that this has actually been folded, and we're showing you 4 bytes across at a time, but this is really a big long stream of bits. Now, let's talk about some of these. Probably won't go into a whole lot of detail on some of them, but they're all very important. And when you get into some advanced security issues, you'll see that even ones that you don't think are very important can be used for nefarious purposes. But starting out here, the first thing you're going to see in the TCP header is a source port. Both source and destination port are both of them are 16 bits. So the range on this in decimal is from 0 to 65,535 in decimal. These are not real ports in the sense that you can't plug anything into them. These do not correspond to ports on a switch, for example. These port numbers are used by the stack or the code on both the sending device and the receiving device to keep up with where a packet came from, what application the packet came from on a particular device, and where it needs to go, what application or service it needs to go to on the receiving device. So that's the function for the source and destination ports. There are big lists of these, the standard usage of these numbers. We'll talk about this. This is terribly important when you're talking about firewalls, because one of the big things we look at is for example, the destination port number, and we use that to decide whether we want to let the packet through or not. That's one of the things we use to decide whether we want to let the packet through or not. So we will return to this concept. So we have a source port, we have a destination port, each 16 bits. So that takes up the first 32 bits of the header. Then we have a sequence number, which is 32 bits. So that's a very large number. I think it's, what, 4 meg? Can't remember right off the top of my head. It's a large number. We also have an acknowledgement number that's 32 bits. We have a number of flags here. These are what we call the flags. And I'll just draw a little line to these. We have a window size field. We have checksum. And the checksum is just for the header. We also have an urgent pointer. We could have options here depending on whether we need to, actually, and then there's some padding. And then finally there's the data here. This is not to scale. You would want, hopefully, to have more data than you have header. You don't have to, but you'd like to. So all the way down through here is actually going to be the data, which of course is the reason you're sending the packet to start with. Now you can look at the TCP header as containing information. It's not unlike some of the information that you would put on an envelope, and then the data would correspond to the letter inside the envelope. Whenever you're sending some sort of message, there's information that you need about the information that you're sending, the data that you're sending, and this is a lot of this is contained in this TCP header. And again, one of the big things we're going to be using here when you talk about firewalls is the source port and destination port ideas. So, more about TCP ports. Again, TCP uses the concept of ports to indicate the application sending data and the application that is to receive the data. Ports are just programming constructs. They're not real in any physical sense, and we're going to talk a lot about ports. Let me give you an example of ports here. If we have a web server here, typically a web service will, we say it listens on port 80. What's really happening is the TCP IP stack in the operating system. What will happen if we send a packet to this computer with a destination TCP port of port 80, the TCP IP stack will pass it to the operating system, and the operating system will check to see if there's a service listening on port 80, or if there's a service that is ready to accept input to port 80. And this would typically be a web server. Doesn't have to be, but it would typically be a web server. So that's the destination TCP port. Would be 80 in this case. Now, let's have a, we'll put a workstation here. And pretend this workstation is going to connect to this web server. And in this case, the source TCP port could be basically any number. Now, it's typically a number above 1023. For example, it could be 3127. For example, the destination TCP port is going to be port 80. Now, you may have noticed that you can actually be connected to the same web server in two browser windows, and the proper information always shows up in the correct window. And I don't know if you've ever wondered how this happens. I do it all the time. I have multiple windows open, going to Google, for example. Here's how this works. We could have another connection to the same web server. In this case, the source TCP port is going to be different than 3127. So this one might be 4914. And I'm just picking these numbers out. That's kind of the way this works. The TCP IP stack, when it needs a source TCP number, it uses something typically above 1024 or down 1023 that isn't being used for any other purpose on that machine. But so that one's is just picked out of the possible range. And again, here the destination TCP port is still going to be port 80. So think about this. I've got two different browser windows on this workstation connected to this web server. It could be google.com, www.google.com. And the proper information is going to show up in each window, because when the web server sends back the response, when the response comes back like this, these numbers get switched. So what's coming back is going to have a destination of TCP 3127. And this is going to have a destination of TCP 4914. So this is how the your computer keeps up with which browser window to put the information in that it receives from the server for a particular request. So you really need to think about this and understand how this works. The port numbers are used basically inside the device to direct traffic to the proper place. Now, from computer to computer, device to device, IP takes over. But once the packet makes it to a particular device, internally, as part of the operating system, we need to determine where that packet needs to go. And that's what we use these TCP ports for. When you're talking about firewalls, we'll actually be filtering on these different, using these different TCP ports. So again, terribly important. You need to think about this till you kind of make friends with the concept. So, I've talked about this previously on this last slide. Port numbering. Typically, the host initiating the session will use a number greater than 1023 as the source port. We often refer to these as ephemeral ports because they change. They're just temporarily used to give us an endpoint to keep up with return traffic. The destination port is usually a number 1023 or less corresponding to a particular service. These are referred to as well-known ports. It doesn't have to be a number 1023 or less. There's just a plethora of applications out there, and we've kind of run out of numbers below 1024. So you can see actual applications that use higher numbers than this. For example, the remote desktop protocol uses 3389, TCP 3389. So this is in general, but it's not written in stone. You can find a list of the well-known ports a couple of different places. If you check on your computer, this is on your computer. It is at least on a XP or Windows 2000 Pro box or Windows 2000 or 2003 server. I'm not sure about Vista. I'm pretty sure it's still there. Under System Root, which is usually WinNT, or sometimes it's Windows, Win32 drivers, etc. There's a services file. This is a file that has a list of well-known ports corresponding to services that could be used on your computer. There's a even more extensive list at the www.iana.org under assignments and port numbers. You can do a Google search on, if you do a Google search on TCP ports, this will be one of the first ones that comes up, actually. And you should do this. It's kind of interesting, and when we start configuring firewalls, you'll need to refer to this from time to time to get the proper port numbers to filter. But you want to keep in mind these are just suggestions. You can configure your web server to listen on a TCP port other than port 80, for example. Some people do this to try to kind of hide their web server. It will hide it from casual users. The real hardcore hackers can still find it, however, and we'll talk later about how they actually can find it. Now, different from port numbers, but still part of the TCP protocol. It's not terribly interesting or useful from the standpoint of well, that's not true. I was going to say it's not that interesting from the standpoint of security, but actually it is, because there's some manipulations to sequence numbers that can have some pretty serious security implications. So just forget about what I was going to say there. Sequence numbers, 32 bits. The number itself points to, well, it corresponds to the first data octet in this segment, except when you're doing a SYN packet. We'll talk about SYNs later. Whenever you see octet, think byte. The octet terminology goes back to the original wording of the RFC. We're going to look at SYN packets. If this is a SYN packet that you're looking at, the sequence number is the initial sequence number. And in this case, the first data octet is actually the ISN plus 1. So that's a kind of a special case. Sequence numbers ideally or the initial sequence number should be randomly generated whenever a TCP connection is established. They're not truly random. They're kind of based on what the previous initial sequence number that was used for the previous, by previous I mean the one that was used for the previous communication session. So they're not truly random, and this causes some security issues later on. Also keep in mind that there are two sequence numbers. If I'm talking to you, I have to keep up with the sequence number, and if you're talking back to me, which you would be, you're going to have a different sequence number. So when I acknowledge, and we'll look at acknowledgement here in a minute, when I acknowledge something, I'm actually acknowledging your sequence numbers. And when you acknowledge me, you're referencing my sequence number. So there's two sets of sequence numbers and acknowledgements, corresponding acknowledgement numbers that are used in any communication session. And we'll do some more work with this possibly later. So here's the acknowledgement number. It's also 32 bits. If the ACK bit control bit is set, this field contains the value of the next sequence number the sender of the segment is expecting to receive. So if you acknowledge me with a number, basically what you're telling me is that you have received everything up to and including the data byte corresponding to the number that you send. And what you're really wanting from me is the data byte corresponding to the next byte you expect from me is the actual byte that corresponds to the acknowledgement number that you send. So, for example, if I acknowledge 101 from you, I'm basically telling you I've got everything up through 100. And the next one I want from you is 101. So, instead of the acknowledgement number being what I've actually got, it's the next one I'm expecting. That's just the way the protocol is written. Somebody just made the decision. That's the way they wanted it to work. One more thing about sequence numbers and acknowledgement numbers. Again, they're 32-bit numbers. This is quite large. But if you start with a sequence number that's a pretty large number, during the course of a session, it wouldn't be unusual for you to get to the end of the numbers that could be expressed with 32 bits. Well, if this happens, what the sequence number does, it just rolls around and starts back through 0, and your TCP stack can understand this, so it's not a problem. It just rolls. It's like a speedometer or something. If you use up all your numbers, you wind up back at zeros, and you keep right on going.